Well, I will give you some information about this project, which is called GINGER. The acronym is Gyroscopes in General Relativity. It was it was presented the first version of this conference, and recently we have been approved some budget, so somehow the construction is expected next year. Anyway, I will tell you something about this special instrument and its connection with fundamental physics and near future plan and conclusions. Dunque, well, in order to explain what is this array, it's not very easy because it is something very multidisciplinary. So sometimes it's very difficult for me to disentangle the fundamental physics for the rest, and also is an interferometer, but it's a special kind of interferometer. And so I have compacted, summarized more or less what the GINGER is in this. It is an array of high sensitivity laser gyroscopes. They are based on a square optical cavity where two counter-propagating modes circulate. The two modes are in general very highly symmetric, and so their interferometry is basically zero. But it is sensitive to any non-reciprocity of the two modes counter-propagating inside the cavity. Very small effects are expected from general relativity, meaning the photon feels, this object is attached to the Earth, the photon feels that it is on top of a planet with a certain mass and with a certain angular momentum. And so on that, we can base our investigation of general relativity and Lorentz violation also. In principle, in the long run, also in non-classical electromagnetism, but we stick on general relativity and Lorentz violation. The larger effect is what is called the Sagnac effect, means that when the cavity rotates, is a non-reciprocity between the two modes, and this is a well-known effect which has been very widely used for develop things for inertial navigation, some very practical application. It is of course a large effect on the Earth surface, and our top sensitivity ring lasers are sensitive to the Earth rotation rate, and so are used also in geophysics, not only in fundamental physics. It is highly disciplinary, as I told you. In fact, our budget now comes from the INGV, the Italian Institute of Geophysics, not only for INFN, which has founded the development of this instrument. And also, you should understand, of course, that the goodness of the instrument is closely connected to the sensitivity it can reach, because we have to look for very small variations in the measurement we have. And the target, I mean, the benchmark to be meaningful for fundamental physics, it is to measure the Earth rotation rate at least of 1 part in 10 to the 9. I mean, all these effects, the new physics is below, it is encoded in the digit of Earth rotation rate, but you have to go at 1 part in 10 to the 9 or even better. This is the object, if you like. I mean, let me see if I can show you. We have 4 mirrors, sometimes are 3. You have an optical cavity. You have a plasma here, an active medium. 2 counter-propagating modes are generated, and we take the interference of the two, and if the cavity rotates with this rotation omega, the frequency, the bit note called Sagnac frequency, it is proportional to the area over perimeter, the wavelength, and omega cosine theta, where theta is the angle between, if you take the area vector and the rotation vector, theta is the angle, so you make the scalar product between the area and the angular rotation. So it is very powerful because you measure the rotation without moving objects, and the proportionality constant, it is a purely geometrical factor. Of course, I mean, as I have told you, there is a large impact in application here. I mean, you see one very small ring laser used for inertial navigation, for submarines, military applications, and so on. But there are few of large area which have a very, very high sensitivity in the world. I mean, there are in Germany, in Italy, in China, in New Zealand, because historically someone, Jeffrey Stedman, pushed for this kind of object in New Zealand, and everything was born here, and then the German people connected to New Zealand. In Italy and in Germany, we developed active ring laser. I mean, it is a laser. While in China, they are mainly focused in the passive. I mean, they don't have the laser inside. There is a reason for that, because the small diffusion of this instrument is due to the fact that this instrument has a very bad reputation. Because it's a very simple. I mean, it's very powerful because you have a laser inside, so it's cheap. But there's a bad reputation because the laser dynamic is nonlinear, and this affects your results. So someone is convinced, or was convinced, that due to the nonlinearity of the laser, basically this object is useless. And so this is the most famous object in the world. It is called the gross ring G inside the geodetic of subset of the cell. It is basically an object like that, a monolithic piece of material with mirrors optically contacted, but it is 4 meters inside. I mean, it is very large, but use the same principle used for applications. Later on, we have this is extremely expensive. Basically, it's extremely expensive because, of course, costs too much, and it's very difficult to handle, very, very heavy. And so it has been developed something. I have here one of our small prototype. You have a 50 centimeter ring laser for goniometer, used as a goniometer, and we have the 4 stations with the mirror inside. Some is a vacuum tank. You have the pipes connecting the 4 mirrors, and somewhere I don't see it. It is in front. We have the active medium and the 2 lasers running. You should see also some red light here, and it is done like that. It is very cheap. In Germany, we have an ERC project for geophysics close to Munich, and they have this 4 rings, triangular shaped. It is very big. I mean, it is 36 meters perimeter, 12 meters side. This was developed for geophysics. Now let's go back to our instruments. This is Gingerino, our prototype in Italy. It is a granite support with the ring laser on top of it. I mean, the 4 mirror holder. Here you see the plasma tube. It is helium, it's red. Let's go on. It is underground located. I have told you that the benchmark is 1 part in 10 to the 9. This target has been already obtained In Gingerino was deduced from analysis that the sensitivity is at least 1 part in 10 to the 9. But this is the result we have obtained using our analysis with the gross ring G. And we see that this is the data of G in 4 hours. In 4 hours, more or less, they crosses the it cross the boundary 1 part in 10 to the 9. I mean, so in 4 hours time, you should be able to reach this target. Impact on fundamental physics. Of course, as I have told you, we measure the rotation rate and this is due to the Sagnac effect. There is a non-reciprocity, not only, but the photon is sensitive to the de Sitter and the lens steering. So it is what you measure is not only the kinematic term, but you have the kinematic plus something else which follow the theory. I will not go in the details because we do not have a single thing. I mean, we have a lot of measurement in principle and several parameters we can check. So the discussion is very, very large and can be found in our paper called Ginger, which is the conceptual design report of our project, which is freely available in the archive, but will soon appear in Memox, which is a journal of the University of L'Aquila. I have only extracted a few slides from last GRM workshop in June by Salvatore Capozziello. It compares what the signal omega s of our instrument from following the general relativity. This is the signal expected in function of the parameter. In this is of the general relativity, and Orava-Lifshitz is similar, but the coefficients of the de Sitter and lens steering are a little bit different. In one case, G and Gn are equal, in the other are different. So, and there are alpha 1 and alpha 2. And so this is, I mean, of course, it is not a trivial stuff, but basically in this way you could access the alpha and see if G and Gn are equal. This is always Capozziello, I mean, more or less always same thing. Just let me summarize that the lens steering has been already measured, but in this case, it is a quantity which depends on the latitude. Generally, it is measured an average quantity. In our case, it is not an average quantity, but it is at a fixed latitude. Not only, we do not need the map of the gravity field to reconstruct this quantity, which is another advantage. There are, of course, a lot of, in principle, in the future, with the data, we can make a lot of tests for the many parameters in the theory and all the alternative theories. Is not going on? Okay. Another thing that can be tested is M gamma, which has been already tested for the FR theories. I mean, some upper limit by gravity probe B and Lawrence. Also, Ginger can make this, and also alpha 1 and alpha 2. This more or less repeat what we have done then. Here there are some papers we have written, but well, of course, there is a large list of papers also for the Lorentz violation, and the target is always one part in 10 to the 9. J. Tasson has studied this problem and also analyzed the existing paper of our prototypes. I mean, the problem is that for the Lorentz violation, our prototypes are horizontally aligned. This is not good for the Lorentz violation. So we need something with a different orientation with respect to the Earth axis. So you found all the literature in the paper I have with our conceptual design. There is also the exercise. We have also done the exercise in the alpha lambda plot. I mean, with the target one part in 10 to the 9 and one part in 10 to the 11 of Earth rotation rate, the exclusion plots of Ginger would be that. Now let's look at the apparatus. We should put, I mean, we have to measure 3, of course, is the optimal. I have told you that these are projectors, so you have at least 3 to well measure the local rotation. And we have a special choice. One aligned at the maximum signal, so parallel to the Earth rotation axis, one horizontal and one outside the meridian plane. So far, we have the budget to build 2 of them. So the one of the maximum signal and the horizontal one. The collaboration is a mixed collaboration with optics people, geophysicists, and some engineer. It is part of the underground geophysics of lab of Gran Sasso. And no, this is an old picture, sorry, it is not Gaetano Luca this afternoon, I'm sorry. Oh, non capisco, I don't know why it does not move. It's not, okay. This is a list of all our papers in the last 10 years. We have addressed all the problems of this apparatus, how to control the geometry, how to, one of the most important part, it is all the work we have done to eliminate the laser nonlinearity from the system. And this is a picture which gives you a lot of information. Because this kind of instruments measure at a low frequency. We measure at the low frequency, and the low frequency has a lot of interesting expected signals, tides, oscillation of the Earth. Most of these signals are well known, polar motion. Most of the signals are well known, and this is the signal we have, of course, this is our outer shed, and the geodetic signal, the lens steering, and all the other fundamental physics are static, I mean, level, I mean, it is a DC quantity. And here we show one of Allen deviation we have evaluated from our instrument. So we are already, with Gingerino, already are reached 1 part in 10 to the 9 with 10 days of integration. But what I want to tell you with this picture, it is that this is a very special kind of apparatus, because we are a very sensitive, very high sensitivity apparatus, but with a lot of signals, well known. Most of them are well known, very static, I mean, always the same. Tides are very nasty objects, but they are repeated itself every day. And this is a big advantage for us, because in this way we can debug our instrument and to check the calibration of the instrument and try to solve the problem. I mean, we have the data to test our apparatus, a sort of natural test area. Recently, we have also compared the data of Gingerino with the GNSS antenna to see if there is some positive signal between the two, which is very, very, very important. It is a single device, so the focus is in lower frequency. It is in a very asymmetric interferometer. This means that we are independent from the typical laser problems as frequency noise, things like that. And the frequency reconstruction is another very important tool, because the frequency reconstruction means that we do not saturate. So it is a very high sensitivity instrument, but we can detect a very high signal and a very small one. Let me show you that. I mean, this is Gingerino during an earthquake. You see the signal of the earthquake, and the apparatus is not affected by that. So it's very robust. I mean, and so we can try to accumulate data for a long time, because I mean, usually very high sensitivity apparatus are a lot of limitation in this respect. But this is because we are based on frequency, and so our measurement rely not at DC level of dark currents and things like that, but on how you scan the time, which is something we usually do with very, very high precision. So why we can try to make this kind of measurements. So it's basically an ideal instrument for low frequency investigation. This is another thing which, in my opinion, tells you a lot. I mean, this is G. Or every time people tell me, but how you can overread the very huge tides, solid earth tides. The solid earth tides is something enormous. The crust raises by 40 centimeters, I have been told. So it's a very huge signal. This is the signal of G, and the big signal here is not the earth tides, the solid earth tides, but this is the polar motion. This is the earth, which moves like that, and the earth tide is this small signal here. So it is a signal. These are 3 days. It's a signal very clean. It's an instrument very clean because things does not rotate, basically. So you can use this the rotation to investigate a very, very low frequency signal with very, very high, very, very low amplitude. Well, we have the general rule we have used to develop our instrument. I mean, to have everything in a thermal bath. Well, I don't want to go. I think it is late, probably. We have used a lot of all the symmetry of the problem in order to not to be limited by the apparatus. I mean, I've used all the symmetry and trying to use the saddle point to be limited at second order, but typical problems. This is, I mean, I'm late, maybe. How much? Yeah, I'm late. We are late. Okay, 5 minutes. Okay. This is our object. I mean, we have a central part in granite, and we have the spacers to isolate the mirrors one from the others. It is in silicon carbide, which is a material, light material, but with very, very, very big Young modulus. I mean, it is, I mean, 3 times the steel. So something very rigid, and avoid couplings between the mirror and another in order to limitate the spurious rotations induced by forces acting on the apparatus. we want to make in this way something closer to that, to G, because right now Gingerino, our prototype, is 20 times worse than G. We have to try to be closer to G, which is almost ideal. The two ring, I mean, this is very important because in this way we can solve the problem of the alignment angle. I mean, because as I have shown you, the signal depends on the rotation, but also on theta. And so, I mean, this kind of signals, a misalignment of picoradians simulate your signal. So you have to solve this problem. So why we have the two ring to determine the theta of the horizontal object. We have the same. We are also developing a small object for called TRIO, transportable ring laser, using the same model. It's the same concept, so the same design, and for this small object, and which should be soon ready, and before the end of the year, we hope, so we can test part of the apparatus, of mechanical apparatus of Ginger. These are details, and it is quite, I mean, we expect to well, I think this is not very important for you. We expect to build this object next year. Well, we will put the orders at the end of the year to collect all the pieces in the second half of 2024. Then the construction will take 3 years. We are trying also, we are a small group, so we are trying also to have with us younger researchers in order to learn all of the technique and to learn directly on the object how to handle and how to prepare things like that, in order to be prepared to give some continuity to this experiment. Let's see. And this is the last part. This is a big debate. We have realized 2 or 3 years ago that the noise of Gingerino, our prototype, was not consistent with the model. I mean, this is an interferometer limited by the shot noise. The shot noise for Gingerino expected a frequency noise of a level of 10 to the minus 11 radian per second, but we have found 2 years ago that was inconsistent with our data analysis. The noise was much less, and later on we realized how to measure directly the noise of our apparatus, the stochastic noise of our apparatus, obtaining something like that here in 10 to the 4 seconds, so 4 hours, we cross the 10 to the minus 14 radian per second, and this is 3 10 to the minus 15. I mean, one part in 10 to the 9 is here, and it's a completely different. This is something we are studying because it's quite important. The sensitivity is one of the key points, and also if it is like that, it does not make sense to make it too big, because it is already very sensitive. And that's it. So we have started to build the Ginger project, I mean, the Ginger apparatus, and in collaboration with the geophysicist. The location should be node B, but it has to be finalized. We are reviewing the details of our drawings, and we hope to set all the orders at the end of the year and to build in 2024. And the data taking should start in 2025, because as soon as the cavity are aligned and the laser are on, this instrument works. I mean, we do not have feedbacks, we do not have anything. I mean, just we keep the apparatus, and thanks also to the underground location, which has a natural thermal stability, usually we can work like that. I mean, eventually we can make some control, but we should be able to take good data as soon as the lasers are active. Thank you.